Sorry?
Yeah, okay.
Yeah. Okay. So let's get started. Today it's my great pleasure to introduce Leon Bottou. Leon Bottou is currently at Microsoft. Before joining Microsoft, he was at NEC Research Labs, and prior to that, he was at AT&T. Leon has made a number of contributions to machine learning, both practical and theoretical. And he's also very well known in the for his work on the deja vu system. So for those of you who use documents in deja vu format, you may or may not know that Leon was one of the main people behind developing deja vu. He's also credited with a number of firsts. From what I know, you did the first practical implementation of an SVM.
The second.
Sorry?
The second.
The second. But, Leon does a lot of work on stochastic gradient learning. And there is a little story that I want to share with you. Whenever a new student comes to my group, one of the first things I tell them is that if they want to sort of learn how to write a good thesis, they should go and read David McKay's thesis. And if they want to learn how to write good code, then they should read Leon's code. So that's actually something that I always recommend all my new students to do. And today is going to talk about stochastic gradient learning.
Hello, does this work? Can you hear me? Yes, thank you. So, well, I have a long summary, and I'm probably going to add some more items if I get time to do it. And I'm first going to describe what it is to learn with stochastic gradient and slowly go to how it performs and why we would want to do that in the first place. So let's take an example, a binary classification. We have patterns X. We have classes Y equal plus or minus 1. So often I write the examples as Z, which is the pair XY. It's just compact notation. So I'm going to build a linear model. So I choose features. So I have a phi of X, which is some d-dimensional vector. And I write a linear discriminant function, which is fw of x is the sign of w transpose phi of x. So, well, we go on. But I guess you all know this. We choose a loss function. Q of zw equals some loss of y, the actual label, f of xw, which is the output of the system. And for instance, you could use the log loss, which is not really a SVM, but it's close enough. We know that we cannot minimize the expected risk. Let's say this EW of the loss over the probability because we don't know the probability. But we can compute an empirical risk. And we can minimize the L2 regularized empirical risk, minimum of W of the regularization term here, and the empirical risk. And choosing lambda, in fact, if you interpret this as a Lagrangian, is the same as saying that W squared is less than B, some constant. OK. The simple way to do it is gradient descent. It's not a very good way, but it's a simple way. You take the gradient of the thing you minimize, multiply that by some gain, and subtract it to the parameter and repeat. This kind of loop like this. Now, the problem of this is that you have this big sum here. So if you have 1 billion examples, it's going to be costly. The stochastic version is very brutal. Instead of having this, you just remove the sum, basically. So at each iteration, you pick a random example, you compute the derivative of the loss for that example, add the derivative of the regularization term, multiply by some gain, and subtract some W. So it's a vast simplification of gradient descent. It's also very noisy because I pick a random example each time, different. But where do I pick the example from to start with? And in fact, you can see two slightly different setups that are very connected. One is the stochastic setup. You have a training set. You draw an example randomly from the training set. But in practice, it's not what we do. We just shuffle the training set and go sequentially. And if you do that, you're going to converge to some optimum that's specific to the training set. And you have the online variant where that's appropriate if you deploy a system in the real world and you get examples from the real world. And instead of drawing the examples at each iteration from a training set, you draw them from the reality. And the same mathematics are going to apply, which can be a bit surprising because overall, the stochastic gradient is going to optimize something that's going to be the mean of whatever loss you take. It's a noisy process, but when I'm removing the sum, I'm basically taking my examples of some distribution, and I'm going on average to do what I would have done if I had the gradient with respect to that distribution. We're going to come to that later. So if the examples are drawn from a finite training set, the stochastic gradient descent is going to optimize the empirical error. If the examples are drawn from nature, then it's going to optimize the expected error. So somehow, we mix the two aspects of machine learning. We can look at stochastic gradient as a method that's going to find the optimum of a training set. This is what's happening when we draw examples from the training set. Or we can look at it as an algorithm that's going to go straight to the best generalization error, and this is what's happening when you draw the examples from nature. And there is this new dual nature that's going to play a lot of tricks in the future. So whenever you write a statement about the convergence of stochastic gradient descent, you also make a statement about generalization, because you can always look at this in that setup and say, well, if I take my examples from the actual distribution, then I optimize something which is the generalization error, not the training error. So I've shown an example of stochastic gradient for the SVM. And the thing is that you can do this for pretty much everything. So I'm just going to go through some examples. So a very first one, that's from the 60s, Widow and Hoff, that's called the Adaline. Or nowadays, we wouldn't call this we wouldn't think too hard about this, but this is practically very important. So the model is a step function applied to a linear, so it's a linear discriminant function. The loss function is the mean squared without the step function. Well, the optimization is a nice little machine like this with an update rule that's absolutely trivial. And this is important because this has been used extremely widely. It's been used in every modem has a system like this that adapts to the signal online. So the Widow and Hoff were signal processing people. Now, you have the multi-layer networks, the ones from the 80s, 90s. The model, I don't know, you all know this? Yes. So the model is this acyclic combination of sigmoid units. The loss is mean squared error, for instance, and you do a stochastic gradient descent. There is a secret that's well kept about multi-layer networks, is that they work. If you look at what people say about machine learning in the typical curriculum, it's a footnote somewhere. People used to do that. But they actually work. They're a bit tricky to make work, but once you know how to do them, they're very useful systems. Now, let's look at the case where the loss function is not differentiable. If I go back to my algorithm at the beginning, I take a derivative here. I'm going too fast. So if at some point I draw a point Z, and this Q is not differentiable. What's the big deal? I just can draw another example. Now, when is it going to work? And I have my derivative of the error, which is the derivative of this integral here. And the question is when to know when the derivative of this integral is equal to the integral of the derivative. And we know that's quite robust, that if Q is not differentiable in a couple points, provided that I have a boundedness condition, this is going to work. So most of the mathematics applies. Most of the math apply if Q is not differentiable in a couple points, provided it's not too bad, provided it's continuous enough. So another example is the perceptron of Rosenblatt. Again, a linear discriminant function with a threshold. And the perceptron historically was made of two layers. There was a first layer that would take an image and produce a feature vector, so that's the phi function, and then the linear discriminant part. The loss is a maximum of 0 and the margin term. So if W phi of x doesn't have the same sign as x, this becomes positive, and then you have a loss. Otherwise, the loss is 0. The maximum makes it not differentiable. Not a big deal. I can compute my gradients. Basically, when this term is positive, I can take its derivative. When this term is negative, it's 0. So basically, by just using the stochastic gradient update, I derive the perceptron rule. K-means. Well, I'm going to have a loss. K-means is the minimum over K of 1/2 of Z minus WK. So K-means is this system where you have centroids, you have examples, and you try to position the centroids in a way that spreads the examples. So the loss means that the distance between an example and the closest centroid has to be as small as possible. So if you write this loss and forget that sometimes it's not differentiable, to compute the derivative, you have to look at which of the centroid is closest. So that's K star. And then you can compute the gradient, which is going to be ZT minus WK star. So it turns out that you can do it quite nicely with a gain that's 1 over NK star, where NK star is the number of points that were on the centroid. And that's what McQueen did in '67. So there is this optimal gain. But that's basically the K-means rule in an online fashion. It's actually very effective. You probably heard about K-means as a two-step algorithm. The step 1 is assign points to centroid. Step 2 is recompute the centroid. This is probably what you've heard. But if you look at the McQueen paper from '67, this is not what he did. What he did was do it in an online fashion. Take a point, look at the closest centroid, move the closest centroid a little bit closer, and take another point and do it that way. And if you compare both methods, you'll discover that McQueen's method is a lot faster. It's a bit more complicated to explain, but it's a lot faster. So learning vector quantization. So this time you have centroids, but they have classes. So you have, let's say, white centroids and gray centroids. And the idea is that when you get a pattern, you look for the closest centroid, and you say the class of the pattern is the class of the centroid. So you can see this as a supervised K-means. And the way you actually do it is that you want to optimize. I'm going to use that now. Yes, it works. So you would like to optimize the number of misclassifications. But the number of misclassification is sort of a step function. Either you're correctly classified, in which case that loss would be 0, or you're incorrectly classified, in that case the loss would be 1. And you can't really optimize this. So you can cheat and do something that could be like this, for instance. So in the case of the centroid system, you have to distinguish two centroids. So you have a point X. You can have a centroid that's closed, that I'm going to call W minus. And you can look at the closest one that has the correct class. So that, suppose it's a black point. So you have the closest centroid and the closest one that's black. And you have these two distances. So there are several cases. First, they could be the same because the closest centroid actually has the correct class. Then these two distances are the same, and you don't want to do anything. So let's call it this D minus and D plus. And look what's happening if you consider D plus minus D minus. If they're equal, you don't do anything. If they're different, that means that the closest centroid doesn't have the right class. So when they're too different, you're going to say it costs 1. And in between, you're going to put a kind of ramp. And that's the meaning of this loss function here. It takes the distance between X and the closest centroid with the right class minus the distance between X and the closest centroid across all classes, divide by some normalization, and produces a ramp that's like this. So anyway, if you differentiate this, you find the LVQ rule of Cohen. Lasso. So at the beginning, I used the SVM with L2 regularization. What if you use the L1 regularization here, this thing here? Now, the L1 regularization is annoying for every optimization algorithm because, well, the L1 norm is not differentiable. And so close to the angle, you have a lot of problems. So there is a trick that's very useful and that's quite old, is to write W, the parameter, as the difference of. So each coefficient of W is the difference between two terms, U1 minus V1, U2 minus V2 to UD minus VD. And both terms are constrained to be positive. So when you write it this way, you can differentiate with respect to the UI and VI, and you get an update rule, and then you project into the positive. So basically, it's the stochastic gradient, but this time constrained to terms that are positive. And that does the lasso quite well. The truth is that it's not going to give as much sparsity as you want, because you have all this noise that checks all the weights all the time, so the weights don't get clamped to 0 that easily. But the value of the function and the quality of the optimum is going to be there quite fast. So I've now said that the stochastic gradient is something that's quite general, can be used for many algorithms, and that, in fact, many classic algorithms are instances of stochastic gradient. And one of the questions is, why do we want to do that? It's such a noisy process. You draw an example, you get a gradient that could actually take you completely in the wrong way, and then you take another one, and you hope that on average is going to do the right thing. It seems to be very complex and impractical compared to state-of-the-art optimization methods. So stochastic gradient is slow. I don't know if you see the ellipsoids there. So I assume I have a kind of cost function, and these are the level curves. At the optimum, well, my partial gradient, so basically I have a total gradient, which is the true gradient, which is the expectation of, actually I should say the derivative of Q, and the partial gradients, which are the gradients of Q. And the expectation of the partial gradients is the expectation, is the total gradient. So if I'm off the minimum, I get I can move in any of these yellow directions with the idea that on average I'm going to do the red move. But if I'm not optimum, I can move away from the optimum whenever I draw an example. So if I'm on the optimum, I draw an example that happens to be misclassified. I'm going to move my weights even though I was at the optimum. And maybe another example is going to drive me back. So I'm sort of flying above the optimum. So this residual noise, it's proportional to the learning rate. Because if I increase the learning rate, I'm going to, so I have my ball. I'm here, and I'm moving in a kind of random fashion, depending on which example I draw, at a distance that's proportional to the gain. So the only way I can actually go to the optimum is if I reduce the gains. Now the problem is that I cannot reduce the gains too fast, because if the gains reduce so fast that the sum form a convergence series, well, I could be on a slope that's continuous, but because they form a convergence series, I'm going to stop at some point. So a 1/t convergence for an optimization algorithm is a catastrophe. Any optimization algorithm does something like exponential minus t, and the good ones are more like exponential minus exponential t. Now, it's also fast. Suppose you have a training set that contains just mistake, 10 copies of the 100 STEM examples. If you do batch, you're going to compute the gradient by going 10 times over the 100 STEM examples. So you're going to do 10 times the work. So if you do an epoch, so an iteration on this full set, well, it's equal to do an iteration over the set of 100 examples, because you get the same gradient, you get the same signal. You just did 10 times the work. If you do that with a stochastic gradient, you don't have this problem. You take examples one by one. So when you took 100 examples, you pretty much did the work that corresponds to the whole set. So basically, if you make a number of iterations that's equal to the number of elements in the large set, 1,000, you pretty much make the equivalent of 10 times what you would do if you do just 100. So this looks a little bit contrived example, but it's also quite realistic in machine learning. We can learn because the training set contains redundancies. We can learn because the examples somehow repeat, somehow are related to each other. So is it fast or is it slow? So this is what I call the anecdotal evidence. So in '57, there was this perceptron, and I think this is Rosenblatt, actually, the real one. So it's worth seeing more closely. First of all, the perceptron is not an algorithm. The perceptron is a machine. And he has in his hand a set of 8 weights. You can see them. Each weight is a potentiometer, so adjustable electric resistance. That's piloted by a little electric motor. So you can see the motors, and so the potentiometers are somewhere here, and these are the motors. And the way the thing learns is that whenever you show an example, it sends the right current to the motors to adjust the weight. And so I wish I could hear the noise of that thing. And this is the retina. So you see, they're recognizing patterns. And you have to be appreciative, because in the late 50s, TV was not really an old thing. Video cameras that were not common. And this is not a USB camera. It was really a serious work. So basically, this is the biggest computer they could afford. So why did they use the stochastic algorithm? Well, they certainly had constraints, like they couldn't store many examples. So they had memory constraints. So It's not because they didn't know better. They knew optimization. Optimization predates electronic computers because in the 19th century or the 18th century, there were computers. They were just human computers. They were even called computers. That was their name. So he knew about optimization. He did that because he didn't have computing resources to do anything else. And the question is, well, does this mean that the stochastic algorithm does more with less resources? And if it does, it's probably a hint. So 88, that's Jan LeCun. And the problem they had in AT&T was to use these new machine learning techniques for doing optical character recognition, but not recognizing things that were anything, recognizing things like this kind of strange digits that clearly are not part of the data set. So that was a challenge. And LeCun and colleagues came with this idea of a convolutional network. That was actually a variation of an idea of Hinton. That basically takes the input and applies a bunch of convolutions, then subsampling, then convolution, then subsampling, nonlinearity, so it's a big neural network. And this idea is actually quite old. In fact, you find it in the 70s by Fukushima, and there was a model of vision by Huber and Wiesel that was like this. So it's actually quite well principled in our understanding of vision. Now, the computing resources were a Sun 3 that you can compare with the Palm Pilot from the first generation, not the modern one, the ones from 10 years ago. And this thing had 9,000 training examples, 2,000 test examples, and that's about 3 weeks of training for the machine. And so did they use a stochastic gradient because they didn't know better? Well, it turned out they knew better. There is another paper of the same period, that Becker and LeCun, that investigates a lot of second-order algorithms, BFGS, basically all the classic optimization algorithms applied to this problem. So he did that because he didn't have computing resources to do anything else. That was already pushing the size of what you could do on a computer of that time. And does this mean that a stochastic algorithm does more for less? So there is another one. I was directly involved with that one. That was 95. And our problem was to read checks. So it's more complicated than OCR because you have to find where the amount is written. You have to cut the amount properly. And you have to recognize each item. Then you have to make sense of what's written there, like star, 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 2, 3, 4, star, 2, 2, stars. And so you end up building a system that's quite complex, where you have several things, where you start with the check image, and you try to find fields, and you try to segment the fields, and you try to recognize what's in it, and you try to apply some grammatical reasoning, interpret it, and get a number. And it turns out that we were able to put all these steps in the context of a single learning machine that we optimized globally. So now the problem was to make it run on our machines. And the machine was, this time, there was a Sun 4, so which is about as powerful as your average cell phone. Not an iPhone, just a regular one. So how do you do that? First of all, it's good to pre-train each of these stages separately. So you get data for fields, and you train your field segmenter. You get data for segmentation, you train your segmenter. You get data for recognition of isolated character, you train a recognizer. And each of the recognizer there is actually one of these big convolutional networks. And so you do that at every level. And when you put everything together, it sort of works. It actually works. It works. You can use that. And then you apply gradient in the whole system with stochastic gradient. And we have about 200,000 segmented digits and about 250,000 unsegmented check images. And the training algorithm is kind of CRF-like. That's actually, the inspiration was the LVQ2 that I described. So basically, you have a lot of choices to make, like field segmentation, recognition, how you apply the grammar. And you compare two things. you compare the choice with the best score and the set of decisions that have the best scores, the best overall score, and the set of decisions that have the best score, but only among the set of correct decisions. And you try to make these scores equal. So why did we use stochastic gradient? Because we didn't know better? Actually, we knew we had SVMs at that time. Because we didn't have computing resources to do anything else, that's for sure. That was pushing it again. And well, stochastic was the way to do it. So this is a work that was done in NEC by Colobert, Weston, and others. It's try to solve multiple natural language tasks. I'm not going to go over this architecture and how it's done, but basically, it's a single system that can do a number of natural language processing tasks, like part of speech tagging, name entity recognition, chunking, parsing in the latest version, semantic role labeling. And it does it in a feed-forward way in one shot, quite fast, actually a lot faster than the classic systems, and with a performance that's about the state of the art. Now, the training set for training the unsupervised part of it was basically all of Wikipedia plus all of Wall Street Journal. That's about 1 billion words. And training was 6 weeks. So if you look for the earlier examples, training was 3 weeks. It seems that after 3 weeks, we break down. We can't wait anymore. And this time was 6 weeks. And the reason was that we just forgot one. So there was a cluster running something. And we just forgot the process, ran for 6 weeks. And at the end, it was quite good. And then we have 1 million words for task-dependent training, but that's the easy part. And that was stochastic gradient again, because we couldn't do anything else. So as a summary, I presented the stochastic gradient. How does it go? And I gave some contradicting evidence for its speed. The first part is that as an optimization algorithm, it looks very slow. The second one is that as a learning algorithm, it seems to have interesting property, like this property to be robust, to be able to take advantage of redundancies in the training set. And I gave anecdotal evidence that in history, in the short history of machine learning, that was a solution of choice when people tried to push the limits of what they can do on the computers of the time. So now it's time to start analyzing the things more precisely. So I'm going to start with a simple case. So one-dimensional f of w is a parabola of second derivative h. And I'm going to look at gradients that have the form gradient of the parabola, which is hw, plus some noise. The noise is going to have a mean 0 and a variance g. So first of all, when there is no noise, it's a useful comparison. Well, what we can do is the gradient descent with gain gamma t equal eta constant. So wt equal wt minus 1 minus eta g. So I can write this because g is hw, wt minus 1 minus eta h wt minus 1. And I get this 1 minus eta h wt minus 1, which is 1 minus eta h to the power t times w0. So basically, if eta is less than 2 over h, this thing is an absolute value less than 1. When I raise it to the power t, it goes to 0. That's the solution. So the plane gradient converges. We knew that. And its speed is exponential, because whenever I add the increase t, I multiply by some value that's less than 1. Well, let's add the noise. So it's going to become hairy. gradient descent with decreasing gain. Gamma t equal eta t minus alpha. I explained before that we need decreasing gains because otherwise it's going to fly over the optimum and never go down. So t minus alpha with alpha some positive number seems a good thing. So I write my gradient and I replace. And my problem now is to estimate Wt squared. I would like that to go to 0. So I just square this and develop Wt minus 1 square minus 2 eta t minus alpha Wt minus 1 hw, okay, plus the quadratic term. And the first thing I'm going to do is take the expectation of this given everything I know up to time t. Meaning that the examples I'm going to draw at time t is my random variable. Everything else is known. So Wt minus 1 is known. Here, Hwt minus 1 is the same. But the noise, well, I have the expectation now. It's going to be a 0, so it's going to go away. And here in that term, I'm going to have the expectation of the noise squared, which is my variance g. And then I take the expectation period. So I get the expectation of Wt square equal Wt square, and I have another one here, 1 minus 2 eta h t minus, okay, times expectation of W square t minus 1, plus an extra term. So if you compare with the previous slide, it's not that different, except that we have this extra term. So how are you going to do with it? I don't like these slides. I wanted to change my slides at the last minute, but I didn't have time to finish. So so I take my thing here, and this I can actually decompose. I can apply it recursively. So what I'm going to have U0 times the product of all these terms, plus, well, each of these terms here is introduced at a step, and then when it's there, it's multiplied by the remaining multiplicand. So sum of I equal 1 to t of these terms here, product the remaining multipliers. So I have these two terms, the green term and the red term. So first observation, when alpha is less than 0, everything diverges, because basically my j to the minus alpha becomes bigger and bigger. And same for that one. So, well, it goes to the infinity, it's no good. We knew that. When alpha equals 0, which would be the case of a constant gain, well, you have to look now, so the j or all these terms go away. And first question is 1 minus 2 eta h plus eta square h square. Is it between 0 and 1? Or this is the absolute value of this less than 1. If it's not less than 1, well, I'm multiplying each time by something greater than 1, so it diverges. So if it's less than 1, well, this is going to go to 0 because I'm multiplying 0 by something less than 1 many times. And if you look here, you can show by the methods I'm going to describe later that this converges but not to 0. So basically, you're in the situation where you're flying above the optimum because you didn't decrease the learning rates. But now we need to be more precise. Let's look at the green term. So the green term is there. I can take its log and forget about log of u0 for now. So it's sum of j equal 1 to t of log of this. Log 1 minus something that gets small is equivalent to the thing itself, plus dot dot dots because there are extra terms. this should be a j here. And now these sums, I can approximate that by integrals. So minus 2 eta h sum of j equal 1 to t of j minus alpha. I'm going to say it's integral from 1 to t of x minus alpha dx. The same for this one. And then I have a constant because, in fact, I should actually bracket the terms between two integrals, the lower integral and the upper integral, and plus something that goes to 0. And if I just apply the integration, I see that when alpha is between 0 and 1, the green term converges. When alpha equal 1, so basically when alpha is between 0 and 1, this term here goes to minus infinity, and this one is smaller in comparison. So basically the log of this goes to minus infinity, means that the green term goes to 0. So the green term converges. Now we have to look at the red term. That's the one I couldn't write yet. So sum of I equal 1 to t of eta square g I minus 2 alpha product of g equal I plus 1 to t of 1 minus 2 eta h g minus alpha plus eta square h2 g minus 2 alpha. And the complexity here that we have to look at several cases. Well, first of all, I'm going to take the case where alpha is between 1/2 and 1. And I'm going to look at this part here. And I'm going to look pretty much like I did here. So it's actually the same, you know. If I take the log, it's the same, except that I start from j equal I plus 1 instead of t. So by using the same thing, I can say that this term here is something like, actually, if its log is something like minus 2 eta h sum from I to t of x minus alpha dx plus, actually I'm going to leave this like this. Because if alpha is greater than 1/2, this is a convergent sum. So this is a constant plus something that goes to 0. So I'm left with this. So if alpha is less than 1, the primitive of this is x 1 minus alpha over 1 minus alpha taken between I and t minus 2 eta h. Plus constant plus O of 1. So I get something like which is minus some constant t 1 minus alpha minus I 1 minus alpha plus constant plus O of 1. And if I take the exponential of this to go back to my product, I get, well, something that doesn't look very pretty. There is a minus here, so I get exponential k I to the 1 minus alpha over exponential k t 1 minus alpha. And the constant of O of 1 means that I multiply by some constant here, plus O of 1. Then I need to insert again the rest of my red term, that thing here. And this is the simple case, by the way. Well, this is another sum, another integral. So I'm going to look at, well, OK. Well, I'm going to look at this now. It's sum of I equal 1 over t of some constant exponential k I 1 minus alpha over I 2 alpha. And that's sort of integral between 1 and t of exponential k x to the 1 minus alpha over x squared dx. And turns out that if you write the derivative of this, you get something that has this shape. Yes, there is alpha, 2 alpha, x alpha here. So the derivative of this is, well, I have x2 alpha below. So g is x alpha. F prime is going to be xk x1 minus alpha times x1 minus alpha, x minus alpha, and there is some 1 minus alpha. There's an alpha going out, a minus alpha going out. So it simplifies here. Plus fg prime. And g prime is, there is something else. Did I mix my, OK. Never do that in front of people. I'll come back to that later. And go back to this. OK, I'm going to do the case alpha equal 1. It's more interesting. So alpha equal 1 is sum of I equal 1 to t. Yes. The derivative is going to be minus k log, because this time I don't derive. So x minus 1, the integral is going to be a log. So minus 2 eta h log t minus log I plus constant plus O of 1. I take the exponential, so I get something like so exponential of this I multiply it by this sum, by this stuff here. So now I have sum of I equal 1 to t of et squared g I minus 2. Yes, good. I to eta h t minus 2 eta h times constant plus 1. So I can simplify eta squared g t minus 2 eta h, sum of I equal 1 to t, I Now, we know that this converges if the exponent here is less than 1. So I have a condition that's necessary. I want eta h should be more than 1. Because if 2 eta h is more than 1, suddenly no, I cannot do it that way. Well, I need to do my integral again. So this is going to be like t, this minus plus 1. You know what? I go back to my slides. So forget everything. Let's go to that thing. So I have ut equal 1 minus 2 eta h t minus alpha plus dot 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 ut minus 1 plus eta squared g t minus 2 alpha. So when alpha is less than 0, everything diverges. When alpha equals 0, I have my two cases. If eta h is greater or equal than 1, this term here has an absolute value that's more than 1. Everything diverges. If it's less than 1, that is going, the product of these terms is going to go to 0. But here I'm going to have some kind of convergence series, and I'm going to have an extra residual term. So when alpha is less than 1/2, this stuff, the sum of this term diverges. And that could be bad enough to cause divergences, so I'm going to eliminate this case. So when alpha is greater than 1 now, I can say that ut is greater. So when alpha is greater than 1, the extra term is a little, is quite small. So I can say that ut is greater than the first part, 1 minus 2 eta ht minus alpha plus dot 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 ut minus 1, which is greater than u0 product of t of this thing. But this time, the log of this product is equal to the sum of the logs. Is going to be equivalent to minus 2 eta h sum of t minus alpha. And if alpha is greater than 1, this converges somewhere. So that means that the error ut doesn't converge to 0. So basically, I narrowed my convergence regime to alpha between 1/2 and 1. If it's between 1/2 and 1, this might converge. Outside, I'm in trouble. Actually, this converges if it's because if alpha is less than 1, this goes to minus infinity, and then we're fine. So I'm going now to take alpha between 1/2 and 1 and define Vt to be t to the alpha plus epsilon ut. And so because this is t alpha plus epsilon u wt square, if I show that Vt goes to infinity, it tells you that the residual error decreases, but not as fast as alpha plus epsilon. Not as fast as alpha. And if it goes to 0, that means that the residual error decreases, but faster than 1 over t alpha plus epsilon. So I can rewrite the recursion in Vt instead of ut. So I have Vt equal this. I have my extra term that appears here, Vt minus 1 plus something like this. And since this 1 plus 1 over t minus 1 to the power alpha plus epsilon is about the same thing as 1 plus alpha plus epsilon over t, I can write my recursion this way. So first case, alpha less than 1. I take epsilon equals 0. And I see here that this term in alpha t minus 1 is actually negligible compared to this term in t minus alpha. So it goes into the dot, dot, dots. So I get my decomposition, which is the same one as the one I tried to write. The green term converges to 0. We already discussed that. And the red term, well, it's exactly the thing I said, except that you have to bracket these two sums with integrals. So this one, the sum over j minus alpha, is going to give you a term in exponential I1 minus alpha. And you have a I minus alpha that comes from here. And this time, the derivative of exponential I to 1 minus alpha is I minus alpha exponential I. So basically, you can do the calculation. And you just show that it goes to a value that's non-zero. Therefore, you get that the ut is on the order of t minus alpha for alpha less than 1. Fine. Now, the case alpha equal 1 is actually nastier, because this time this t minus 1 term cannot be neglected compared to this alpha. So you need to consider this green thing here. So if epsilon is less than 0, this red term here is not going to annoy us, because, well, it's going to be multiplied by a lot of things that are less than 1. But the sum of the red term by itself would converge. So it will go to 0. Now, we also need this green thing to be positive, because if it's negative, the multiplier is greater than 1, and we're in trouble. So if 1 plus epsilon is less than 2 eta h, Vt goes to 0. If 1 plus epsilon is greater than 2 eta h, then Vt goes to plus infinity. Now, if epsilon greater than 0, you can show that Vt goes to infinity because the red term wins here. And the idea of the proof is the same. It's develop everything, write the two terms, and to bracket the j minus 1 with integrals. And in that case, it simplifies nicely. So you find that when alpha equal 1, ut is t to the minus minimum of 1 and 2 eta h, meaning that you use eta too small, you're in trouble. So after messing up my calculation multiple times, and I have to clean them up, I'll clean them up and I put slides with everything spelled out. I'll do that. It's going to be ready. So you get that the best convergence speed you can achieve is the expectation of the squared error on the parameter is in 1 over t. So this is achieved with a gain that has the form eta t minus 1. You should make sure that eta is greater than 1 over 2h to the second derivative. Otherwise, the convergence can be slow, much slower than t minus 1. Or alternatively, you can decrease the gains a little bit slower, because if you use a gain of the form gamma t equal eta times t minus 1 plus epsilon for some positive epsilon, you go almost as fast, and you don't have constraints on eta. And the question now is, how good or bad is this convergence speed? So for an offline optimization algorithm, this is very slow. The batch gradient descent had something where this was like exponential minus t, because we multiply each time by some term less than 1. For an online optimization algorithm, so let's go back to the situation where we draw examples from the nature. The quadratic minima, suppose you have examples that are just numbers, and you want to minimize the sum, the average sum of the number xi minus w squared. So W is going to go to the mean of the numbers. And if you do it that way, the convergence in 1 over t is perfectly reasonable, because to estimate the mean of a set of examples, if you see t examples, you expect to have the mean with accuracy 1 over square root of t, or the squared of that error should be 1 over t. So that's right. So this speed of convergence, it's slow for an offline optimization algorithm, but if you look at it in statistical terms, it's correct. It's going to estimate the mean at a speed that's consistent with statistics. So, yeah, I think I would like to stop here, and I'm going to fix my slide with the right calculation. And I'll continue tomorrow. What you said?
We'll take a 5-minute break and come back for the second hour.
Oh, what time is it? Oh, that's right. I just did everything in 1 hour? That's crazy. Okay, I need a break for sure.